Swayam Prabha. Digital India. Educated India.
The new module, we are going to be talking about randomized linear algebra. RLA for short. So, in randomized linear algebra, the aim is to be able to handle very large scale matrices. As we saw in the context of Johnson, Linden, Strauss embedding, our aim is to be able to compress large objects into a smaller object. While doing this, we try to preserve as many of the properties as nearly as possible. That is the whole aim. So, linear algebra enjoys lots of well known, very well tested, time tested algorithms for solving many problems of interest. So, linear algebra deals with quite a variety of algorithms for solving problems. What are the problems in linear algebra? I want to be able to solve Ax is equal to b. I want to solve linear least square problem z is equal to h of x. I want to be able to solve Ax is equal to lambda x, eigenvalue problem. So, solution of linear system, linear least square problem, linear eigenvalue problem. These are some of the major problems in linear algebra, and much of the computations in science and engineering deals with one or more of this class of problems. So, these problems are very interesting and important in applications. While we know very good algorithms for solving these problems, deterministic algorithms, when the problem size becomes larger and larger and larger, as it happens when you go from conventional small data set to big data set, the time required to solve large scale problems, even when the efficient deterministic algorithms are known, are very large. So, just to be able to illustrate, if I want to multiply two 2 by 2 matrices, the time complexity is we have to perform the order of n cube operations. We all know that the standard inner product based computation requires n square inner product. Each inner product takes 2n operation. So, the total number of operations involved to multiply 2 by 2 matrices of size n is 2n square, 2n cube. Suppose if n is a million, n to the power of 3 is 10 to the power of 18. This is the total number of operations I have to perform. This total number of operation, I want to find out how much time actually the wall clock time it takes. So, let us assume a teraflop machine. That means it takes 10 to the power of minus 12 seconds per operation. Therefore, if I multiply 10 to the power of 18 times 10 to the power of minus 12, that is equal to 10 to the power of 6 seconds. That is a millisecond. you can readily see there are 60 seconds in a minute, 60 minutes in an hour, there are 24 hours in a day. So, if you divide 10 to the power of 6 by 60 times 24, you can roughly see this is of the order of 11.5 days. I want you to be able to verify this computation. This is roughly of the order of 11.5 days. So, what does it tell you? I know the algorithm. I have well established mathematical software to compute to multiply the product of two matrices. But if I have a big data matrix of size million by million, to be able to just multiply these two matrices alone is going to cost you 11.5 days. Will you be able to wait for 11.5 days to perform one operation in your program? Your program may involve lots of other operations as well. So, your program may take weeks to complete. Herein lies the challenge. Can I make sure my computer is fault free for weeks? If the supply of electricity blinks even for one cycle, if one bit of the calculation changes, the whole entire calculation becomes waste, it becomes erroneous. To avoid that, now we have uninterrupted power supply to protect the variations in the grid voltage not affecting the computer. We have the intermediary, which is called uninterrupted power supply, that protects it. So, assuming all other things are equal and good, the only question is that are we ready to wait for weeks and months to solve one instance of a problem? The answer is no. We want quick answers. So, in order to be able to get quick answers, what are the results? Either get more powerful computers, but teraflop machines are some of the most powerful computers on the face of the earth right now. Yes, there are petaflop machines, but they are few in number, and these computers are very expensive. So, except those organizations, governmental organizations, where they have very nearly unbounded resources, government has a lot of money, so they can afford to spend more money. So, one way to be able to tackle big data problem is to go in for larger, more powerful computers, so that I can solve large scale problem in a shorter time. The alternate approach is, the problems given to me are large by nature. I would like to be able to shorten the computation time. One answer is to be able to reduce the dimension. Here comes the idea of randomization. So, randomized algorithms are good tools to solve problems approximately very fast. This method of randomization comes within the family of algorithms called Monte Carlo type algorithm. Monte Carlo type algorithms are characterized by the fact that they always find the solution. The accuracy of the solution depends on the number of samples. Monte Carlo algorithms were introduced into the computing arena in the early 1940s. It was developed by a group of mathematicians and physicists who were involved in the design of atomic bomb. They were interested in integrating very complex multiple integral. They could not evaluate those integrals in closed forms, so they resorted to numerical approximation. So, there are a whole group of numerical approximations for evaluating integrals. Monte Carlo method is a randomized algorithm that is very helpful to be able to evaluate complex problems very easily. So, that is the notion of randomized algorithm. So, randomized linear algebra deals with a family of randomized algorithms that helps to approximate solutions to large scale linear problems by clever reduction of dimensions of the matrix problem, matrix related problems, and that's the essence of the entire area of randomized linear algebra. The randomized linear algebra is very new, evolving. It is hardly 20 years old in its 25 years old in its in life, and I am sure there are lots of very interesting questions waiting to be addressed. So, in this module I am going to provide you a glimpse into the world of randomized linear algebraic algorithms. So, what is the starting point? Large scale matrices. Where do these large scale matrices come from? We have already seen the sources of big data. So, a large scale matrix A is a m by n matrix. There are n objects. You can view in two ways. We can say the rows denote the objects, the column denote the features, or vice versa. The column denotes the features, objects, and row denote the features. Until now, I use the column to denote the object, the rows to denote the features. For the sake of completeness, I am now trying to assume the objects are given in a row and the features are given in the column. Really does not matter which way you look at it. So, if x is one way, x transpose the other way. So, instead of dealing with the matrix x, I may deal with the matrix x transpose. That is all the difference. That is all the difference. So, Aij, jth feature of the ith object. There are m objects, n features, m by n matrix. Geometrically, the objects are points in the n space. I can think of this matrix to be a representation of m objects in the n dimensional space. The objects are point. I am assuming m, the number of objects is less than the ambient dimension n. This is very similar to the problem that we considered earlier. I have a set of objects u1 to un. I have a set of capital N objects lying in a d-dimensional space. There we assume the capital N is less than d, the ambient dimension. So, you can readily see the relation between the previous treatment and this treatment. These have tremendous areas of applicability. In astronomy, objects may be different angular regions in the space. I want to be able to look at the sky, and I am going to divide the sky into different sectors, which are each one of them are angular sectors like that. This is one sector, this is another sector, this is another sector, and I am going to be looking at astronomical object in various sectors, and that is what astronomers essentially do. So, objects in different angular regions in space, and when you observe, you are observing the energy radiated by those objects. So, the features are elements in the frequency band. So, in this region I am getting signals in this frequency band. In this region I am getting signals from this frequency band. So, does this signal is in the visible region, is in the X-ray region or infrared region? They try to be able to look at the features as frequency bands of the received signal in those by object, the received signal, the signal being emitted by objects in these different sectors. So, that is why we are able to identify here is this is the bearing of that object, this is the bearing of that object, and so on. So, large matrices can come from astronomical observations. In genetics, the objects are the list of genes, human genome, plant genome, they have already been mapped. genomic project is one of the greatest international projects that has come to full fruition in the last, over the last 3 to 4 decades. So, the level Aij is the level of the ith gene in the jth individual. So, the objects are individuals, the gene expressions of different individuals. So, if I want to be able to arrange objects versus the gene expressions, so you get a good matrix Aij. Aij is the matrix where the number of rows denote the objects, the number of rows denote the objects, and the number of columns denote the features of the genes. That can also come from document or text analysis. The object could be a list of documents. What is a list of documents? I want to be able to analyze the editorial write-ups in a particular newspaper to understand whether they are biased or not. So, I would like to be able to understand the sequence of editorial by a given newspaper over time. So, let us pick a 6 months interval, daily editorials. So, that is a list of documents. The editorial office, they express their opinion on anything and everything that happens around them. What are the features? An editorial is essentially a text. Let us assume it is an English newspaper. There are English alphabet, there are English words in the dictionary. Every text uses words from the English dictionary. If I assume the number of words in the English dictionary, let us say 25,000, I do not know, I have a Webster's unabridged complete dictionary as of 1975 in my office table. Language is not a static device, it grows. We do not use several of the words that were prevalent in Shakespearean time today, but we also introduce newer words. So, what is the list of all the words in English literature? Which of these words occur in a particular editorial and which word occur how many times? So, Aij is the frequency of the jth term in the ith document. Frequency of the jth term in the ith document. What is the term? Term is a word in the English language. So, I am trying to digitize, I am trying to represent a digital representation of a document by simply a vector that consists of frequencies of words that occur in that write-up. If a word does not appear, if the word in the dictionary does not appear, the entry is 0. If a word appears 7 times, the entry is 7. Then you can compute the total number of words in the editorial. Generally, editorial lengths are fixed. They write very succinctly to express their ideas within a constant space. So, the length of the editorial is fixed. I would like to be able to find out which words are used how many times. If you divide the total number of words by the frequency, by the number of times a word occurs, it is called the frequency. So, that is called frequency distribution of words in a given document. So, every document is represented by a vector, represented by a row vector, and I have a collection of 6 months of daily editorial from a given newspaper. The number of words in the dictionary is large, is probably 25,000, 30,000. Even if you assume I have a 6 months of daily editorial, that is only hardly 6 times 30, which is 180 to 200 items. So, I have 200 objects, each of them have a feature which is more than 25,000. So, that is what is called the document representation. The matrices come from discretization of ODE and PDE. In numerical analysis, we would like to be able to solve differential equation. Only a very small number of differential equation can be solved in closed form. Those are simple exercises. They are meant to understand the methodology of solving differential equation. Quite a large fraction of problems that arise in applied sciences, engineering, the equations are nonlinear. They can be ordinary or partial differential equation. It is very difficult to solve them in closed form. So, we generally use numerical approximations. Matrices also arise as kernel matrices in describing pairwise relations. For example, if I have n objects, I can, so I have a data matrix first X, I have m objects, each of them have features 1 to n. So, this is called a kernel matrix K. The kernel matrix K has an entry Kij. Kij is simply the inner product of the ith row and the jth row. Please understand, ith row is a representation of the ith object, jth row is a representation of the jth object. The inner product between the ith row and the jth row is an entry in the matrix K. Such a matrix are called kernel matrices. They represent in some form similarity matrices. They are pairwise relations. You remember in Lindenstrauss lemma, we are interested in preserving the pairwise properties of objects. So, this is one application where pairwise properties of objects are of great interest. So, these kinds of matrices are used in trying to understand the similarity between objects. So, X is the given data matrix, this is the derived matrix, kernel matrix. The derived matrix can be large. So, these are at least 5 examples from astronomy, from genomics, from document or text processing, discretization of ordinary and partial differential equation, kernel matrices in machine learning. What are the properties of these matrices? The data matrix. These data matrices are generally rectangular. Rectangular matrices, eigenvalues, they do not have eigenvalues and eigenvectors are not defined for rectangular matrices, are defined only for square matrices. But we have extended the notion of eigenvalues to singular values. So, the eigenvalue of the Gramian is the singular value of the original data matrix. These matrices X, the data matrix are such that the Gramian X transpose X and XX transpose, depending on whomever is a smaller Gramian or a larger Gramian, we compute the eigenvalues of the larger Gramian. And if we assume X is a full rank matrix, the Gramians are symmetric and positive definite, we could expect all the eigenvalues to be positive. Even though the eigenvalues are going to be positive, if the minimum eigenvalue is very close to being 0, its square root is even is also closer. So, the singular values are such that they may decay very fast. If these singular values of X decay very fast, which is also, so this is the singular value plot, this is the eigenvalue plot of the Gramian, eigenvalue of Gramian. If the eigenvalues plot like this. So, these two together tell you that I can compress or reduce the dimension. Please understand, this was the basis for PCA. We have already seen this in PCA. So, when is dimension reduction possible? The dimension reductions are possible if the given data matrix X is such that the eigenvalues of the Gramian either decrease fast, which is equivalent to saying the singular values of the matrix X also decay very fast. This fast decay is a signal that there is a lot of noise in here the noise corresponds to the flat region of the plot. The steadily fast decaying part refers to the signal. This part corresponds to noise. So, it is this ability to be able to distinguish, separate noise from the signal is a fundamental necessity for being able to decrease the dimension. And this was the basic idea that was introduced in PCA, and we are going to fall back on that fundamental idea. And so, we are going to be able to utilize these properties to get a reduction in the size of the matrix. So, that is the source of, so we talked about the source of large matrices, we talked about conditions necessary on the data matrix for that will allow dimension reduction. So, let us assume I have a class of matrices that indeed exhibit that property of fast decreasing singular values. So, I would like to be able to find structures. What is the structure? I want to be able to find the structure, the signal component, the structure that corresponds to signal, and this we are going to explore with the notion of randomness. Earlier in PCA, we exploited the rate of decrease of lambda, we chose a beta, we sought a value of k such that the sum of the largest k eigenvalues divided by the total sum of the eigenvalue will be greater than or equal to 1 minus beta. If that beta is small, we know using k modes, each mode corresponding to an eigenmode. So, using k eigenvectors and eigenvalues, I should be able to recover 99% of the information if beta is 0.1. So, that is the idea. Here I would like to get similar results by walking along a different path. So, that is what is called discovering structures in large matrices using randomness. This is essentially a two-step procedure. In the first step, I construct a low dimensional subspace that captures the action of a matrix. Please understand, matrices are linear operators. They map objects from one space to another space, linear transformation. So, if this is Rm, if this is Rn, if A is a matrix that maps Rn to Rm to Rn, A maps Rm to Rn. So, what does it mean? If there is an x, if there is an y, there is an A, so y is equal to A of x. So, I am interested in the action of x. The action of x provides vectors in R capital N. So, one way to understand the properties of matrices is to understand its action. The action of a matrix results, this is the domain, this is the codomain or range. I can understand the action of a matrix. I can understand a matrix by its action. So, if n is less than m, that is called the dimensional reduction. So, construct a low dimensional subspace that captures the action of a matrix. So, this is understanding the range space of a matrix. Understanding the range space is equal to understanding the actions of matrices. The second one is to think of project or restrict the matrix to the subspace and process the matrix using the standard factorizations. So, look at that now. In the first step, we construct a lower dimensional subspace that captures the action of a matrix. So, we come from the original space to the subspace of smaller dimension. So, once we identify that lower dimensional subspace, then we project the original matrix or restrict the original matrix to this subspace and process using standard algorithms in linear algebra. So, this is the general framework for randomized algorithm. Identification of the subspace that captures the action of a linear operator. The subspace is of smaller dimension. Once you identify the subspace, then project or restrict the matrix to this subspace. So, I want a new representation of the matrix that operates within this lower dimensional subspace. Once I get that, the randomization is over, the classical linear algebra takes over. So, the first step is randomization, second step is classical linear algebra. That is why it is called randomized linear algebra, randomization. So, I would like to be able to elaborate these two fundamental concepts. So, stage 1, compute an approximate basis for the range of the input matrix m by n. So, if I have a m by n matrix, it maps Rm to Rn, Rn, it maps Rm to Rn, where n is less than m, and this is the matrix A. And how do I do that? I want to be able to, so if I want to be able to describe a subspace, a space can be defined by the basis. Every subspace has a basis, and if a subspace, if I am looking for a basis, orthogonal bases are better than non-orthogonal or oblique basis, because algebra in orthogonal bases are simpler. So, I am going to seek an orthonormal basis, and where the basis, how do I represent the basis? It is represented by a matrix of size Q m by R. Please understand, I am working with the matrix of size m by n. I am going to, n is the space of the range. So, the action of A are found in Rn. I would like to compute the approximate basis for the range of the input matrix A. The range of the input matrix consists of the entire Rn. Please understand, the entire Rn, if the matrix A is well defined in the sense of it is a full rank matrix. So, now instead of concentrating on the entire subspace Rn, I am going to be look for a subspace of dimension little r. So, Q is an orthonormal matrix. There are two relations you need to be able to verify quickly. Q transpose Q is IR, Q transpose is a projection matrix, orthogonal projection matrix. Please remember, if H is a matrix of size m by n, the orthogonal projection matrix induced by H is given by H transpose, H transpose H inverse times H transpose. We have already seen this is to be the orthogonal, this is to be the general projection matrix for any matrix H. But if I set H is equal to Q, if I set H is equal to Q, and where does this come from? This comes from the least squares theory we have already seen, and that is the reason why I did modeling least squares theory in great detail. So, if I set H is equal to Q, which is m by R, Q transpose Q is identity. So, Q transpose Q inverse is also identity. Therefore, PQ now becomes QQ transpose, which is the M by M matrix, which is an M by M matrix. This M by M matrix is a projection matrix. So, you can think of this Rn to be a subspace of Rn. So, what is that we are interested in? So, another way of looking at it is, I have a bigger space, I have a smaller subspace. So, I have a bigger space Rm, I have a subspace Rn. I want to be able to project objects from the bigger space to the subspace. So, if an object remains in the subspace, it is in itself, there is no need to project. If I am having an object in here, I need to project. Projection is done by projection matrices. We are interested in orthogonal projection matrices. So, the orthogonal projection matrix into the subspace of size Rn, I am sorry, R to the power of R. So, look at this now. The matrix A maps objects from Rm to Rn. Now, I am going from Rn to Rr. Right, that is the picture I want you to have at the back of your mind. So, in principle, I should be interested in the entire Rn, but if the singular values of A are decreasing very fast, maybe the action of A in the range space is essentially restricted to the top A eigen subspace, the top R eigen subspace, and that is what we have learned from PCA. So, this is an analogy, this is an idea that borrowed from PCA, and I would like to be able to implement this idea. So, I would like to represent A approximately equal to QQ transpose A. That means, this is the projected value, the projected A, this is the original A. I want to be able to approximate A by this projected A, where R is small, but large enough to be able to capture the action of A. I hope you all understand the basic concept from this picture. So, I can rewrite in two ways, one like this, another also like this, Rm to Rn to Rr. So, the matrix A takes object from m dimensional space to n dimensional space. The range is entire Rn. If the singular values are decreasing faster, the essence of the action of A is confined to only a subspace within Rn, and I would like to be able to identify the subspace. I would like to be able to identify subspace by identifying a basis for the subspace. The basis for the subspace consists of columns of the matrix Q m by R. I am seeking an orthonormal basis. Once I get an orthonormal basis, I can project the matrix A into that subspace. So, this is an approximation of A on the left hand side by the projected A on the right hand side. So, finding Q is fundamental. Finding Q holds the key for approximation. Now, if I found such a Q that satisfies the relation 1 in here, then we can use Q to get the standard factorization of A. And what am I talking about standard factorization? Here again I need to explain this a little bit more. Please understand, many of the application problems that arise in engineering and science are reduced to either solving Ax is equal to B or solving Z is equal to h of x, Z is equal to h of x, or solving Ax is equal to lambda x. Here A, H, they are all large scale matrices. So, much of the problems are involving solutions of linear system, solutions of least square problem, solutions of eigenvalue problem. In our module on modeling, we have already discussed at great length methods of solving linear system, methods of solving least square problems. All these problems involved several types of factorization, LU factorization, LD, L transpose factorization, Cholesky factorization, QR factorization, singular SVD, singular value decomposition. So, many of the classical algorithms are expressed in terms of multiplicative factorization. So, multiplicative factorization is a big bulk of the algorithms in linear algebra to solve many of the standard problems, and these class of algorithms are called direct methods. There is a corresponding indirect methods. We have already talked about that when we were doing modeling, especially matrix decomposition module. The iterative methods involve additive decomposition. So, I am now going to confine myself only to the direct methods of solving linear systems or linear problems, and that is why the standard factorization of A comes into play. So, stage 1, stage 2, they complement each other. Stage 1 is realized as a randomized algorithm, stage 2 is a deterministic algorithm. Stage 1 is implemented by a randomized approach. This randomized approach can be based on one of two types. One is called random sampling, another is called random projection. These are two fundamental approaches to solving large scale numerical problems in linear algebra by way of dimension reduction to bring about efficiency in computation time. So, we are going, so the key thing is approximate, and that is nothing new in analysis. We all want to go for gold. If you can't go for the gold, we settle for silver. If you cannot settle for silver, we settle for a bronze. If you do not get a bronze, at least you have the pleasure of having participated in the Olympics. The same idea here. We want to be able to solve the problem in the best, we want to get the best solution in the least possible time. If that is not possible, I am going to settle for a good approximation. So, good approximation means what? I should be able to compute the solution faster, but the approximation should not be too crude. So, I need to be able to attain two objectives. The quality of approximation should be good, the time should not be too large. So, what is the idea here? Can I have the cake and eat it too? So, I am not going to settle for any faster algorithm. I am interested in fast algorithm that will guarantee certain performance measures. Quality of approximation is very important while trying to achieve approximation solutions. So, that is the ultimate idea. So, our goal is twin goal. One is to be able to obtain the solution faster, and the approximation must be good. This goal can be achieved by a two-stage procedure. Stage 1 is to be able to identify the basis for the subspace that captures the action, that captures the large fraction of the action of the original matrix A. Second, once we identify the basis and obtain the matrix Q, I replace the matrix A by QQ transpose A. So, QQ transpose A is the new representation of A in the subspace of interest to me, and then I manipulate that A. I use that A of smaller dimension or smaller rank to be able to obtain approximate results I am seeking. So, the stage 1 is implemented a randomized approach. There are two approaches for randomness. One is called random sampling, another random projection. Stage 2 uses the standard deterministic approach. Why is that? Digital computers came in 1950. Ever since, mathematicians and algorithm analysts have developed tons and tons and tons of algorithms to be solved, to be able to solve quite a variety of problems. Linear algebra is a major component in this mathematical software development. Packages that are MATLAB and all the other packages in every programming languages, they solve many problems in numerical linear algebra. I don't want that investment to be a waste. So it is this ability to separate the randomized component and the deterministic component working together hand in hand to get good approximate result in a reasonably shorter time is the ultimate achievement of the modern theory of approach to randomized algorithms in linear algebra. This separation is the key to the success of this approach. Now, I am going to provide an example of this approach to SVD computation, singular value decomposition. We have already talked about the deterministic approach to singular value decomposition when we are talking about least square problems. So, now you see the reason for doing extensively the coverage on least squares approach, because that helps you to derive several of the algorithms of interest in linear algebra, and I am going to fall back on many of the problems and try to approach it in a new possible way by bringing in this two-stage procedure: first stage randomness, second stage deterministic. So, let us work out the problem. Let A be the original matrix of size m by n. Let Q be the basis for the subspace, and Q is the matrix of size m by r. So, Q is the matrix of rank r. So, that means I have decided to get a rank r approximation to A. And where do I generally get r? R is essentially related to how fast the singular values decrease. You may say, yeah, you did not know what the value of r is. So, if a matrix is of dimension, let us say 10,000, let me say, hey, I would like to be able to do a preliminary analysis by approximating it by a matrix of rank 1000. So, by approximating a 10,000 by 10,000 matrix by a smaller rank, I would like to be able to see how much of the action of the original matrix I can recover from the subspace. So, R is a rank which is already, the value of R is already decided by you. Q transpose Q is IR, QQ transpose the projection matrix. I want to be able to pick the basis which are columns of the matrix Q. So, I am going to consider the projection of A. So, this is the approximation. Here I would like to be able to rewrite this by setting B is equal to Q transpose A. So, A is a matrix, Q transpose A is R by N. I can represent this factorization like this: A is equal to QB. So, it is a kind of a multiplicative factorization. This gives you a low rank factorization. So, what is this? I am having a low rank approximation of A expressed as the product of Q and B. Now, compute the SVD of B using the standard procedure that we have already talked about. Please remember, B is a matrix of size R by N. R is smaller than N. So, B is a broad matrix. B is a broad matrix, 1 to R, 1 to N, R is less than N. So, this corresponds to an underdetermined system. Computing the SVD of H, we have dealt with both when m is greater than n and m is less than n. So, we are going to fall back on that SVD and let U tilde sigma V transpose be the SVD of B. Once I get the SVD of B, then I can define U to be Q U tilde. So, A is equal to QB and B is equal to U tilde sigma V transpose. Q U tilde is U. So, I got U sigma delta V. This is the SVD of approximate SVD of A. So, this should give you an aha to start with. How I can use this two-stage framework to be able to find good approximations for SVD. So, we described a framework for dimension reduction using randomized approach. There are two possibilities. One is by random sampling, another is by random projection. Those are the two tools that have been developed over the years. The random projection matrix has the same flavor as randomized matrix that we used in Johnson-Lindenstrauss embedding, that we multiply a large vector U by a broad matrix and reduce the dimension, a broad matrix X, reduce the dimension. So, that is the same idea of random projection. So, here I would like to be able to talk about the word projection. Projection, orthogonal projection, oblique projection. You all know the notions of orthogonal projection, oblique projection from within the context of least squares. Now, here by multiplying a vector by multiplying a vector on the left by a matrix, I am going to get a new vector, and that transformation is also called projection. So, you may think of this projection as random projection, maybe a misnomer sometime, but we are stuck with it. So, it is called random projection. Why it is called projection? It is projection of a larger dimensional object into a smaller dimensional space. So, projection here more in the context of mapping. There are two approaches. One is fixed precision approximation. In the fixed precision approximation, you remember I wanted to get things fast, but not at the cost of quality. So, I would like to be able to maintain the quality of approximation. So, given A and an epsilon greater than 0, I want to seek a Q with orthogonal columns, and a K which depends on a parameter epsilon, which is the approximation parameter. And what is that I want? I want the norm of the difference between the matrix A and its projection. Please remember, this is QB. So, QB is the reduced representation, reduced rank representation. So, here I am reducing the dimension of the subspace. That is what we are trying to do. And so, the norm of the error must not be greater than epsilon. So, this is the control on the error control. I would like to be able to control the error, and this error depends on the choice of K, which is the target rank, which we called R earlier. So, the dimension K of the range of Q captures the action of A. So, even though A could be a full rank matrix of rank n is larger than K, because of the reduction, fast reduction in the singular values of A, in analogy with PCA, we now have come to recognize that using a K rank approximation, I can capture very nearly the full rank action of the matrix, and the quality of approximation is decided by, is pre-specified by U, the user epsilon. That is a measure of tolerance. So, if you know the quality of approximation you need, you can then find a k that will render the quality as in equation 3. And what does this mean? The dimension k captures the range of Q, the action of the matrix in the range of Q. SVD furnishes an optimal answer to this fixed precision problem. That means the precision is fixed. For each j, we already know what is sigma j. Sigma j's are the singular values of the matrix. The singular values are going from 1 to n. The first, so if I am going to find an approximating matrix X to the matrix A, and I want the norm of the error in the approximation to be less than or equal to sigma j plus 1. What is sigma j plus 1? This is the j plus 1th largest eigenvalue of the singular values of A. It is decreasing, sigma n being the least singular value. So, what is it we are interested? I am interested in finding a rank j approximating matrix X such that I want to be able to minimize the norm of the error to be less than or equal to j plus 1th singular value. And where does this j plus 1 singular value as an upper bound comes from? That comes from the SVD consideration, which we already talked about at great length when we talked about population based PCA. So, now you see the importance of having PCA, having least squares done well before doing the randomized algorithm. So, they constitute the deterministic bulk of the algorithm, the deterministic algorithms for the bulk of the problems. And when we apply those algorithms to large scale problems, we first randomize, get an approximation and apply those algorithms. So, understanding deterministic algorithm in least square algebra, in linear algebra is absolutely fundamental to a better understanding of randomized linear algebra. So, by choosing Q X is equal to Q transpose A, where Q is the m by k matrix with k orthonormal columns, and these orthonormal columns are going to be the left singular vectors of A that guarantees 3. What is the 3? The 3 is the epsilon upper bound. So, now you can see how the whole thing fits in. I have brought in the notion of quality of approximation. Another one is called the fixed rank approximation. So, in here I am seeking the rank j, for which in 4 I am trying to find a rank k matrix, a matrix X of rank at most j, of at most j. So, I am trying to find a matrix X that will satisfy this. So, that is the fixed precision approximation. So, there I fix the precision and look for an appropriate approximating rank. On the other hand, I can have a fixed rank approximation given A and a k. Somebody gives you the k as an input. Then I am going to have to develop a sampling procedure, which we will describe in great detail. That the guts of one of the randomized algorithm, and a parameter p greater than 0. So, you give me a k for a given A, I am going to associate a parameter p integer greater than 0 such that I would like to be able to construct Q with k plus p orthonormal columns. Earlier we said that if k is R, I computed m by R matrix with orthonormal columns Q. Here I am going to construct a matrix Q with k plus b orthonormal columns such that A minus QQ transpose A, which is the projection of A, this is the error, the norm of the error is equal to the minimum among all matrices of rank, all matrices X of rank less than or equal to K, such that the norm of the error is the minimum value, and this error in approximating Q by QQ transpose A will match that K rank approximation as we described earlier. So, these are the two ways of approaching. One is to, so what is the essence of it? One is to specify K and find Q, another one is to specify epsilon and find K. These are two complementary approaches to finding the orthonormal columns of Q. So, how randomness helps to solve this fixed rank problem? That is what we are going to be talking about to start with. So, we seek a basis for the range of A with rank K. So, that is the idea here. So, let W be a random vector, W be a random vector of dimension n. So, I chose a vector in the range space Rn, which is W, and I chose to be random. Y is equal to A times W. Y is equal to A times W is a random sample from the range of A. So, I want you to think of it like this now. This is Rm, this is Rn, here is W, here is Y, this is A times W. So, Y is a part of the range of A. So, if I pick W as a sample from the domain, Y, which is AW, is also a sampling from the range. So, I am now trying to talk about the randomization through method of sampling. So, you pick K number of Wi's in the original space Rm, you compute the corresponding Yi's. So, let us build a collection of random images, K random images Y1 through Yk in the range space. Because W are in general position, the Y's are also going to be general position. So, I now got a matrix Y, which is Y1, Y2, Yk. So, this is a matrix of size. This is the matrix of size n by k. Please understand, I am operating in the range space. So, what is that I have? I have a random sample who are in general position in the range space obtained by mapping a set of corresponding random elements in the original domain space, Wi mapped to Yi. So, now I have a matrix which are the images under A of the random objects in Rm. Now, I have this set of random vectors obtained in the range need not be orthogonal. So, I am now going to orthogonalize the matrix, columns of the matrix Y. Now, please understand, this orthogonalize is a non-trivial step. You may remember we have what is called Gram-Schmidt orthogonalization procedure. Gram-Schmidt orthogonalization procedure. So, given any matrix irrespective of where it comes from, if the matrix are in general position, that means they are linearly independent. Given a set of linearly independent vectors, I can always orthogonalize it. I can always orthogonalize it. So, that is one way to get the columns of Q. Let us go back now, relate this to what we have already talked about. Q is going to be the orthonormal columns of a subspace of the range space that I am trying to work with as an approximation to the whole range. So, I would like to be able to find that basis. I am going to find that orthogonal basis by virtue of generating k samples randomly in the original space and looking at their images. And these images in general need not be orthogonal. So, I orthogonalize it using the well known deterministic Gram-Schmidt orthogonalization procedure, which we have already talked about at great length when we did QR transformation in least squares theory. So, let us now express, let B be a rank K approximation to A, E be the error in the rank K approximation. So, A is equal to B plus E. So, you can think of E as a perturbation matrix. You can think of B as a matrix whose columns are going to capture the dominant singular vectors, and E corresponds to the noise component in analogy with PCA. Please understand, the PCA idea is very fundamental and is very beautifully used as an undercurrent in this development. So, if I now consider Wi, I can consider Yi. So, Awi is Bwi plus Ewi. I am K is given, I am going to pick a parameter P. So, K plus B is the number of elements I am going to sample. So, I have K plus B samples. The goal is to find the basis that covers B. The goal is to find the orthogonal basis for the range of B. Please understand, the error E shifts the direction of the sample vectors. So, B captures the action of the vectors within the subspace I am seeking. E tries to throw the vectors outside that subspace, outside the range of B. This can prevent the span of Y to cover the range span of B. That means the error in the approximation, we have to have a good control. So, in principle, you should be able to have K samples, but in order to be able to cover those things, those information that is going outside the range of B, I am trying to do an oversampling parameter P. So, it is tried to cover slightly a larger subspace, even though I am interested in the subspace of dimension K, I am working with dimension K plus P. This enriched set of K plus P orthogonal column vectors is meant to reduce the leak of information outside the range of B. Please understand, that is the key. That is a very simple idea. It's a neat idea to be able to reduce the information that is getting leaked out of the range of B, because the error space is going to throw the vectors outside the range of B, So, please understand, Yi remains on Rn. So, the information in Rn is captured by information in Rk plus something lies outside. I would like to be able to capture the flow of information outside of the range of B. Therefore, in trying to build B, I do not want to simply restrict to K, I am trying to oversample. This oversampling parameter is meant to get a tab on the leak of information outside the range of B. Small p generally helps. It has been found in practice, p is equal to 5 to 10, generally works very well in numerical algorithms. This is the basis for randomized algorithm. Now, you get a framework for randomized algorithm. How do we implement the stage 1 or the step 1 of the randomization? Please let us go back and recall. The stage 1 is to get an approximation to the action of A by computing the basis Q of the range space where most of the actions of the matrix A lie.